So I stopped the recording and resumed the recording because I wanted to this to a different video. So magnetism. So the schooling magnetism পড়াইছে?
Yes sir.
ঠিক আছে। আমি বেসিক কিছু স্টাফস নরমালি বলে যাই, যেগুলা খুবই সিম্পল স্টাফ, আর হচ্ছে যেগুলা আমাদের মানে এগুলোতে ডিসকাস করার কিছু নাই, মানে these are some sort of stuffs which are the underlying principle. আচ্ছা, here's the thing. We're gonna see magnetism, electromagnetism, and electromagnetic induction, and some parts about the practicality chapter where we go about the live neutral wire and some other physical equipments that we use for our everyday use, like circuit breaker, electric bell, and so on and so forth. All of those use some sort of electromagnetic properties. Now, in the magnetism chapter, there are a lot of information which are given as a information period. So what I'm trying to mean is that there are a lot of what informations in the magnetism chapter, not the why. So for example, I'm going to tell you that any magnet always show up with two opposite poles on its two opposite sides. Maybe not opposite sides, at least it always shows with at least two poles, north pole and south pole. By wrong magnetization or by intentional magnetization, we can make an object to have more than two poles. That's possible, but you cannot make an object that will show up with only one pole. That's what I'm going to tell you. Why is that? Why can we not have monopole? That is not answered in your syllabus. I'm going to tell you that like poles repel and opposite poles attract. Why? I'm not going to give you the actual explanation of that, which actually requires a bit of a quantum mechanics explanation. It can be also expressed by Gaussian surfaces. You don't have those things. Then we're going to represent the working of magnetic behavior by means of some imaginary lines which we call magnetic field lines, where we'll explain the property with the idea of magnetic field and imaginary space where the magnetic force is experienced. And all of the magnetic field is a physical location. Magnetic force is also a force that can be experienced, but the magnetic field lines are absolutely imaginary stuffs. Magnetic field lines are just a way to represent the effect of magnetism in some sort of tangible way, so that our eyes could visualize it, so that our mind could get a grasp on it. It's very much similar like whenever we draw vector diagrams, we represent a length of arrow to represent a vector. That vector might be velocity, that vector might be acceleration, that vector might be force, that vector might be momentum, but we represent a length of arrow to represent a vector. So somewhat similar to that. And then I'm going to tell you that whenever charged particle moves, they produce magnetism around them. I'll tell you that, and you have to believe me for it. I'm not going to tell you why does it do that. We're going to cover that how can we have that property that I just said proven. We're going to see some experiment that yes, moving charged particles actually does produce some sort of magnetic effect. We're going to see some experiment that whether it is true or not, that we're going to cover. We're going to see that how can we make that effect of moving charged particles to produce a magnetic field around them for our benefit. We're going to see about some equipment design and some practical application of all those things. We're going to see those. But why does the moving charge particle or moving charge produces a magnetic field around them? I'm not going to give you that answer. So the part that I want you to understand, that we're going to learn something of this much knowledge. We're not going to learn too much deep. We're not going to learn too much high. For example, electromagnetism or magnetism can be used in linear accelerators and also in cyclotrons and synchrotrons, which are actually some mechanism by which high-speed particles are made to hit each other so that they break apart and give rise to more subatomic particles, which are done in the CERN in Switzerland. And so magnetism has a lot of use in those things. We're not going to discuss those. And why magnetism happened, I mean, what is the underlying principle behind that, what is the type of interaction that gives us to magnetism, we're not going to discuss that either. So if I try to represent the whole knowledge base regarding magnetism in line, we're not going to get into too deep stuffs. We're not going to see too much higher above part. We're going to see the part that fits our understanding level, which is called O level. So I mean, এই জিনিসটা তোমাদের এইজন্য বলছি that you might feel curious, you will feel curious, you are supposed to feel curious, and you might ask me that, sir, why does this happen, or why should this happen? In many cases my answer would be, I'm not going to tell you, or I might tell you I don't know because I honestly don't know. I didn't bother to know because I don't have to, or maybe it was too complicated for me and for my brain to hold on to. I might have read it at some point of my life and my brain decided not to remember this. So that can also happen. So that's that. But I'm going to cover everything in pretty high detail that is required for your syllabus volume, and that is required for you to be to answer questions and be able to understand at your level what is needed. That I'm going to do. But a lot of the why questions will remain unanswered. এই পার্টটু বুঝা গেছে কিনা?
Yes, sir.
আচ্ছা, it's not a bad thing that you don't have a lot of whys. I mean, because it's just the starting of your understanding for magnetism as a new topic. So starting by baby steps is always a good thing. All right. So the way I usually start the magnetism chapter is this, that there are 3 elements which show really strong magnetic behavior. These 3 elements are iron, cobalt, and nickel. These are all found in earth crust. Among these 3, iron is most redundant, most available, and easy to extract as well. That's why for most cases of magnetic requirements, we always prefer to use iron. Cobalt and nickels are used for other purposes where they are exclusive. Cobalt and nickel are not usually used for magnetic requirements. These 2 materials show very strong sensitivity towards magnetism, so sometimes they are called ferromagnetic materials. This is a word, ferromagnetic material. This is just I mean, if we want to divide everything, every type of substance that we see around our world in terms of magnetism, there are 3 different types. You don't have that division in your syllabus. I'm just still telling you. We have ferromagnetic materials, which are these 3 elements, or anything that is made up with these 3 elements. For example, iron's oxide, they also represent magnetism, but not all oxides. For example, ferrous oxide is the iron oxide that shows strong magnetism, whereas ferric oxide or basic moricha, it doesn't show much of magnetism either. Whereas pure iron, or iron as a metal which is not oxidized, does show strong magnetic property. So there are ferromagnetic materials, and there can be paramagnetic materials, and there can be paramagnetic, and there can be diamagnetic materials. You don't have to know this name, but you have to know this name. So these are the 3 types of classification that we have. Then the next information is that magnetism is a property that can be induced within substances. I mean, if an object is if we can have a magnetic material that is not currently magnetized, and we can make an object to behave like a magnet. That's the process that we call magnetization. Or we can make a magnet that is currently a magnet to act not like a magnet. That's called demagnetization. So there are individual processes that objects which has the capability to become magnet, or they are already magnet, they can be made into one to other. So we can make an object to behave like a magnet, or we can make an object not behave like a magnet, provided they have the inherent capability to work as a magnet. So what I'm trying to mean is that you cannot make a piece of plastic into a magnet. You can make a piece of iron into a magnet, or you can make an original magnet, previously existing magnet, to lose its magnetism. So if you have, if some object has any of these three things, or mixture of these three things within its constituents particles, then it's gonna show us magnetic behavior, and we can make it magnetized or demagnetized as we want. That's one thing. There are two different types of poles, North Pole and South Pole. North Poles and South Poles are named after the two poles of the Earth, because on the very early days, the lodestones, which are actually some rocks which are enriched with ferrospheric oxide, which is the iron oxide that is highly magnetic. The sailors use those things to use as sort of compass. They would hang this by a thread, or they'd place it on a plate on a water surface, and that could rotate freely based upon the Earth's magnetic field line, and that would help them to navigate through the seas, oceans. So from that point, the two opposite poles of a magnetic object are defined as North Pole and South Pole, which is actually defined by the geographic North and South Pole. But technically, the magnetic North and South of Earth is actually reversed. I'll show this to you in properly. Here's the thing. Let's say this is Earth. This is the North Pole, geographic North. This is the South Pole. The idea is that if we hang a piece of magnet on the surface of Earth, let's say I'm holding this in the equator, figure not drawn to scale. If this magnet holds true in this orientation, we're going to call this end the North Pole side, and this end the South Pole side. The head that aims to the North Pole is North Pole. The head that aims to the South Pole is South Pole. Now, if I hang it from here, it's gonna look like this: South over here, North over there, just like that. Now, the question is, why does a magnet align itself so that it can actually locate the North Pole and the South Pole? Why does it happen? Why should a magnet do that? This behavior, that why should a magnet align itself with a certain known location or with a certain known orientation, this is explained in terms of the idea which we call magnetic field lines. Magnetic field lines. What do you mean by magnetic field? The space of physical, the region of physical space around a magnetic object within which it can affect another object magnetically. Affect another object magnetically means it can produce produce a force of attraction or produce a force of repulsion onto another magnetic object. That region of space is what we call a magnetic field. It's very much similar to electric field or gravitational field. The idea is very simple. I mean, what do you call a gravitational field? The region of space around a mass within which it can attract another mass object. That region of space is what we call the gravitational field of that object. What is called an electric field? The region of space around a charged object within which it can exert a force of attraction or repulsion onto another charged object is called the electric field around that object. Similarly, magnetic field, the region of space around a magnet within which it can exert a force of attraction or repulsion onto another magnet is called the magnetic field around that object. Magnetic fields are represented by magnetic field lines. Any fields can be represented by field lines. Magnetic field lines are always drawn with curved lines, and field lines come out of North Poles and get into South Poles, because whoever decided to draw field lines in that manner decided it's going to be that way, and it has been that way. There is no hard and fast logic that why magnetic field lines should come out of North Pole or South Pole. The pioneers decided that way, and we still follow that way because there is no harm in following that, and it's not incorrect per se because it was based upon no physical requirement. It was a choice, someone made that choice, and we're okay with it. So let me just find some picture. This is a nice one. It's too small. Stop. See all the figures over here. This is the actual representation of magnetic fields over here. Fields have a couple of properties as well. The key properties of a field lines is that closer field lines represent a stronger field, farther apart field lines represent a weaker field. For magnetic field lines, magnetic field lines come out of North Pole, they get into South Pole. Close to the pole, the field is very strong because the field lines are very close to each other. Far away from the poles or in the equatorial region of the magnet, the field is the weakest. And then we have field lines never cross each other or intersect each other. They always repel each other, so on and so forth. So the idea is that whenever we have a pre-existing magnetic field, so let's say I'm gonna draw a bar magnet over here. So let me just take all these images. So let's say here we have a bar magnet with this magnetic field lines around. So these are, let's say these are the pre-existing field lines. Now let's say we're going to check the orientation of these field lines by using a smaller magnet, which we can say it's a test magnet, or sometimes it's also called a needle magnet, which are really small magnets. Let's say we're going to use a much smaller magnet of this much side, which also has north and south pole. So what we're going to do, let's say if I am going to hang this small magnet by a piece of thread and bring this up on anywhere onto this object. Let's say I'm going to do that. So if I bring it up over any location, this thing is going to rotate in such a way that it will align itself with the magnetic field lines of the exact location. So if I hang this magnet right over here, let's say right over, actually, let's start here, right over here, this magnet is going to work, is going to align itself in this orientation. It's going to be balanced at the center point because of my hanging thread, but it's going to align itself in this orientation such that the south pole would be facing the north pole side for attraction, and the north pole would be facing away from the further away from the north pole because of repulsion. So this end of the north pole, which I'm representing to be the north pole, and this end of the south pole, which is represented as the south pole of the small magnet. South pole and north pole would be attraction close to each other. North pole and north pole would be repulsion further away from each other. That's how they're going to work. If I place it in any other place, for example, if I place it right over here, maybe the same thing will happen. South pole would be close to the north pole, and north pole would be further from the same. The idea is that the way your syllabus actually describes this is that any magnet placed in a pre-existing magnetic field will always align itself in such a way so that pre-existing magnetic fields can very easily pass through that magnet. So any magnet behaves in such a way so that south pole always takes in the magnetic field lines and north pole gives out the magnetic field lines. So it's gonna take in the magnetic field lines, place the magnetic field lines to the south pole, maybe a couple of them, and it's gonna give out the other magnetic field lines on the north pole, so that the whole distribution of the magnetic field lines is least disturbed. If that doesn't happen, we can have another type of variation, which I'm going to show you. For example, situation like this. This was a pre-existing parallel magnetic field, and we have a bar magnet that looks like this. Here they have represented the bar magnet to be very simple field lines. Inside the pre-existing magnetic field line. So if you wonder what is this thing, I mean, what is this thing? Whenever we are considering a figure like this, what we need to assume that this actually can be attained by having a really large north pole over here. Maybe made by a solenoid, and a really large supple over here. They are so big that the field lines in between can be considered to be almost parallel. And if we now bring a bar magnet into this thing, the total magnetic field is going to behave in this manner. Have a look. All the field lines which were initially going in straight line, they're going to bend somewhat, and they're going to enter these people have messed up the arrow direction of this part. I think whoever made this image just was not that much careful. Okay, this image has a little bit of messed up arrow direction. I'm going to correct those arrow directions. So bear with me. South pole should be receiving the field lines. So all of the field lines entering, finishing at the south pole should be flowing inward. Inward. And everything that is leaving out from the north pole, they'll be outward. So the rest of the figure is all right. So field lines which were essentially going this way, they're going to enter through the south pole, and eventually they're going to travel to the bar magnet and eventually go out. And this bar magnet, which produces its own magnetic field, you can see over here, now that field earlier used to have a shape like that, a bit lombate. Now it has become really squashed because of the effect of the this parallel magnetic field line. So that's how the combination figure looks like. If this does not happen, let's say I'm going to show you that this is the most convenient way that this bar magnet can exist within this magnetic field. What if this was not the case? What if this was the opposite way around? That can be shown in another figure. I believe I can find this. Yes, for a solution like that. Where is that?
স্যার আপনি কি কথা বলছেন?
শুনো, আমার এই এমনি করে সার্চ করে পড়াইতে অনেক সময় লাগবে, প্লাস আজকে এমনিতে 11টা বেজে গেছে। আমি ম্যাগনেটিজম পড়ানোর জন্য রিলেভেন্ট ফিগারগুলো সব জোগাড় করে রাখবো। কালকে ক্লাস আছে না? হ্যালো হ্যালো কিডস,
Yes, sir. Yes.
কালকে ক্লাস আছে আমার?
Yes, sir. কালকে আসেন।
কালকে কটার সময়?
কালকে হচ্ছে
5:30
ঠিক আছে, আমি এই ম্যাগনেটিজম পড়ানোর জন্য যা যা ইমেজ লাগবে সেগুলো সব জোগাড় করে রাখবো, যাতে করে পরের ক্লাসে আর গুগল থেকে বেশি ঘাটাঘাটি করতে না হয়। তো I'll call it a day for tonight. Thank you.
স্যার
হ্যাঁ বলো।
স্যার বাকি বইগুলো কবে পাবো?
1 week.
আচ্ছা স্যার।
Thank you.
স্যার আপনি যে বই ম্যাগনেটিজমের বইটা দিয়েছেন ওখানে তো নোটসটা দেন নাই।
এই মেসেজটা মনে হয় মামুন করছে মোস্ট লাইকলি। আমি ওকে আলাদা করে বলে দিচ্ছি যাতে করে সবগুলা নোটস দিচ্ছে আলাদা করে বুকলেট বানিয়ে রাখে। তোমরা যারা ওয়ার্কশিটের সাথে নোটস পাও নাই গিয়ে বললেই হবে, সে আলাদা আলাদা নোটসগুলো সব প্রিন্ট করে দিবে মোস্ট
আর
লাইকলি।
হচ্ছে
বলো।
আর হচ্ছে গিয়ে থার্মালেটটাও পাইনি নোটস।